Welcome back. This will be our final video in this mini-series on simulation-based estimation techniques. And in this video, I wanted to do something a little bit different. I wanted to cover a little bit about Bayesian sampling as a way of simplifying the estimation of parameters in likelihood-based models that are quite complicated. This material links back to some of the videos we covered in prior mini-series on mixed logit, where we talked about the EM algorithm and the MM algorithm. The similar ideas are going to happen in this video as a way of simplifying this estimation of a complicated likelihood function. And if you're like me, you might be a little bit scared or unsure about Bayesian statistics. I've never taken a formal Bayesian statistics class, but that doesn't mean that we can't learn something that advances our knowledge a little bit and gives us a greater appreciation for what the professional Bayesian statisticians do. Let's revisit the mixed logit probability formula from a past mini-series. So here we've got our familiar logit probability function, and the main issue is that we have this individual specific gamma parameter that we don't know the value of for every decision maker in our data. And so we need to integrate it out according to its density. And in particular, we don't have a closed form for this integral, and so we have to solve it numerically or approximate it numerically. And the approaches we talked about in the context of the mixed logit was quadrature or Monte Carlo integration. And the issue with these two methods is that convergence can be slow, or we can have lots of local optima. So it can just be difficult to maximize the likelihood when this is entering the likelihood. So now we can think about what the Bayesian approach does. So what the Bayesian approach is doing is we're not actually going to maximize the likelihood function, but instead we're going to calculate distributional moments from the posterior distribution once we've conditioned on our data. And we'll go through what that means at a high level momentarily. So the key insight of the Bayesian approach is that we're treating these gamma i's as individual parameters that are entering alongside the mu and the sigma, right? So if we go back to this, we have mu and sigma are the distributional parameters of our mixing distribution. And so the Bayesian approach says, well, why don't I just treat these gamma i's as parameters to be estimated as well? And so what we're going to do is something called data augmentation. So the posterior distribution is going to augment our data in a predictable way. And then instead of trying to maximize a complicated likelihood function, we can instead just draw the posterior values of those gamma i's directly. When we condition on the data, that's what we mean by the posterior distribution. We don't have to simulate any choice probabilities. We just evaluate the logit formula at those posterior drawn gammas, and that will give us the choice probabilities that we need for estimating the parameters and so forth. So effectively, we're directly estimating the gamma i's, recognizing that they're coming from some distribution. That's the mixing distribution. And I wanted to draw a connection between what I just described and the EM algorithm, because the EM algorithm is a form of Bayesian statistics. In the EM algorithm, we're making some other assumptions. We're assuming that the gamma I is a finite mixture instead of a continuous distribution, but we're treating it as latent. And we're basically filling in values for gamma I instead of integrating them out. So that's basically what we're doing in the EM, where we treat the type as known and then estimate assuming that we know the type. And in Bayesian statistics, this is known as Gibbs sampling. And so we're doing something very similar there. So in the EM algorithm, which we've already covered in another video, at the E step, we calculate the posterior values of these gamma i's effectively, conditioning on the data and the parameters of the model at that step. And then we maximize treating this as observed. And this will converge to the maximum likelihood estimates, which is what some of the papers that we covered in that set of videos established. With the Bayesian approach, we do something called Gibbs sampling, where we draw the gamma i's from the posterior distribution, and then we're going to draw the mu and the sigma from the posterior distribution as well, conditioning on the gamma i's. And this posterior mean is going to converge to, or approximately converge to, the maximum likelihood estimate in the limit. So you can think of this Gibbs sampling as a continuous generalization of the EM algorithm that we covered in a prior video. So the main idea is that the EM algorithm is going to do the integral analytically through these weighted likelihood components because it's a finite mixture. And then the Gibbs sampler is going to sample according to something called Markov chain Monte Carlo, which we're not going to get into in this video, but it's a way of doing this sampling that's going to incorporate what's known about the posterior distribution. So what's the procedure if we wanted to estimate a mixed logit using a Bayesian approach with Gibbs sampling? We're going to iteratively draw from these conditional posteriors. What are the conditional posteriors? Well, it's these P distributions here. We get a posterior distribution given the current estimates of mu and sigma and the data, which includes the choices and the x's. And we just need to evaluate the logit likelihood at those values. We don't have to do any integration. Then we're going to, given the values of these gammas that we have, we're going to draw mu from this conditional posterior, and then we're going to draw sigma from this conditional posterior. And then we're just going to repeat this until we get convergence, meaning that the posterior means don't change across iterations, just like we would with the EM algorithm. So how does this work at a super high level? How do we know what these posterior distributions are? Well, we get them from Bayes' rule. So the posterior distribution is proportional to the prior distribution times the conditional likelihood, where we are looking at the likelihood of the data given the parameters. And so for this gamma I distribution, we're not going to have a closed form for this posterior. We're going to have to do accept reject sampling through something called Metropolis Hastings, which again, we're not going to get into in this video. I'm just trying to give you a high level understanding of how this works. And then for mu and sigma, there's a couple of different ways we could do it. We could assume that they have certain distributions that are conjugate, which means that the posterior is going to be a predictable distribution based on what we assume the prior distribution is. And then in that case, we could just directly sample from the posterior, but usually people don't want to assume these restrictive assumptions on the priors. And so they might use what's called like an uninformed prior, or a different type of prior that doesn't have a conjugate. And so what's going to happen there is we would still need to use Metropolis Hastings for estimating the mu and the sigma as well. So all we do is a bunch of sampling. We don't do any estimation. We just sample from the posterior. But finding that posterior is actually non-trivial, and so we've come up with this accept-reject sampling scheme called Metropolis Hastings that tells us what exactly this posterior distribution looks like that we can sample from. And then once we just get the average of that posterior conditional distribution, then that's the answer for our estimate. So what are the advantages of doing a Bayesian approach? We don't have to do any maximization. There's no convergence criteria. There's no nonlinear optimizer being called. And we also don't really need to worry about the starting values, because that's going to sort of work itself out as we go through this Markov chain Monte Carlo process. We don't need to let the number of simulation draws grow with the sample size. We get the full posterior distribution of gamma I, not just the point estimates, which is a benefit. And it's sort of recognizing that these gammas are part of a mixing distribution, so it's going to give us the mixing distribution. And in the limit, this is going to be asymptotically equivalent to maximum likelihood estimation according to this theorem by Bernstein and von Mises. What are the disadvantages? Well, there's a different type of convergence issue. There's something called burn-in that we have to avoid. All that's saying is that the posterior that we settle on might be sensitive to the starting values that we provide it, and so we need to let the algorithm run for several thousand iterations before we really tell it to start paying attention, and that's called a burn-in period. And then for some specifications, this Bayesian approach might actually be slower than the frequentist or the classical analog. So it's important to know what the trade-offs are to be able to make an informed decision about whether a particular approach is going to be useful for your use case. I hope you enjoyed that crash course in Bayesian statistics and Gibbs sampling. I have a greater appreciation for what Bayesian approaches can bring to the table in terms of simplifying econometric estimation, and I hope you do too. And more importantly, I hope that you've found this mini-series to be useful in understanding how GMM and simulated method of moments and indirect inference all fit together with the likelihood-based estimation that we've primarily focused on in these videos. Can't wait to get into the next set of videos, and I'll see you in those.